All right, the next section is 12.4, which is the cross product. It is a different type of, I'll say, quote unquote, multiplication. It's a different type of product defined on a vector space. So here in 3 dimensions, the cross product, v cross w, is found by computing this symbolic determinant. For those of you who know linear algebra, then you know that this is sort of pretty nonsensical to have vectors in components. That's why I say symbolic determinant. This happens to, if you just follow it as you would a normal determinant, this does end up producing the correct thing. So this is more or less a way for you guys to compute the cross product easily. So as a reminder here, what you do, first of all, let's talk about a 2 by 2 determinant. So let's write this right over here. So the determinant of a 2 by 2 matrix, let's say this matrix has A, B, C, D for its entries, is written as this. Instead of square brackets, we just have vertical bars. This is AD minus BC. We are doing these two multiplied together, and then we subtract these two multiplied together. A 3 by 3 determinant is found by, if you cross, so we're always going to cross out the top row, but then we'll move this along and do this in 3 steps. So step 1, delete the first column. You're left over with this 2 by 2. So then this will be equal to V2, V3, W2, W3 times I hat. Minus, so this alternates here. It goes plus, minus, plus. We'll have another determinant here. Deleting the top row, always. Now we delete the second column. We're left with these entries here. Oops. These entries here, which give us V1, W1, V3, W3, J hat. Alternating back to plus. We'll have another determinant. Of course, we'll delete the top row as always, and this time the third column, leaving us with this. V1, W1, V2, W2, K hat. All right, so that's how we calculate the cross product. Once we have this written down, we then can use our what we know about calculating 2 by 2 determinants, which we just put right here, and get the full cross product. So another formula for the cross product is that the magnitude of the cross product is length of v, length of w, sine of theta, which is really similar to the formula we had. So I'll just say compare, contrast with what we had for the dot product. V dot w is equal to the length of v times the length of w times the cosine of the angle between the two vectors. So important thing here to note is that this left-hand side is not just v cross w. It's the length of v cross w. A common mistake is I'll see students say that this is equal to this. This is a scalar, right? Magnitude of a vector is a scalar. Magnitude of a vector is a scalar. Scalar times scalar times scalar. This right-hand side is a scalar quantity, so this left-hand side has to be a scalar quantity. If you write v cross w, then this is a vector. So a vector cannot be equal to a scalar. So be careful of this. The cross product is something that is called anti-commutative. In other words, if we reverse the order in crossing, we get a negative sign. So it's not commutative. It's something that's a little bit different called anti-commutative. Nice thing about the cross product is that it forms what we call a right-handed system, in that if we take a vector v and we cross it with some vector w in that order, v cross w, then the vector v cross w is a vector that is perpendicular to each of these. Something like that. So this blue vector is v cross w. It's perpendicular to each.